Quietly.
So hi everyone, welcome to SpaceLink's Story of the Stars Hangout today. We're really lucky to be talking to some students who are having Space Week in Coverdale class today. And later on tonight, we're going to follow up with another hangout about the scale of the universe. So that should be really fun. So I'm going to start my slides. If you can tell me if you can see them, that'll be great. And also anybody who's watching on YouTube, if you want to pop down the name of your school that's watching, that'll be great, because that's really good for us to know who's watching. So I'm going to share the screen now. And can you see my slides?
Yes, we can.
Okay, brilliant. Oh, no, not that one. There we go. That's perfect. So today we're going to talk about the story of the stars. So I wanted to start by asking you a question and ask if anybody knows, what is a star?
What is the star coming there? Noah?
Is it a ball of boiling lava and fire?
Okay, great. Anybody else want to answer? Owen?
A giant ball of gas.
Thank you. Freya? You're going to agree with that? Anyone else think something different? Oh, okay. Did you hear those answers?
Yes, I did. Yes, so those are really good answers. A lot of people get a bit confused about what a star is, because we have lots of things in the night sky that kind of look like stars. Sometimes it can be something that's human made that confuses us, like the lights from a satellite or an aeroplane. Also, we've got things like planets that shine in the sky and look like stars. And to us, mostly stars look like little pinpricks of light. And one of the good ways to tell the difference between a planet and a star is that stars appear to twinkle and shimmer, whereas planets will be more of a steady light. And planets are quite easy to confuse with like aeroplane and satellite lights, because they seem like a steady, bright, shining light. So one of the brightest stars that we can see further away in our sky is called Sirius, and that's a very bright star. But obviously we have a star that's a lot nearer to home. Does anybody know what our nearest star is?
Oh, nearest star. Sunny? The sun? Anyone think something different? Fred? Betelgeuse. Harvey?
It's the North Star.
The North Star. Anyone got a different idea? No?
Oh, fantastic answers there. So the first answer was right, that our nearest star is the sun. And we often don't think of it as a star because it's so much closer. So it doesn't look like the other stars. But the sun is our nearest star. Then we have a system close by called Alpha Centauri. And so that's nearby. And that's about 4 light years away. And other people there mentioned Betelgeuse and Polaris, which is a North Star. They're very bright stars in our sky, but some of those are quite far away. And we'll come back to that a little bit later. So yes, what is a star? A star is a very large ball of bright, glowing hot matter in space, and our nearest star is the sun. Now, somebody mentioned a ball of gas there, which is very close to the truth, but actually there's another state of matter that we're going to talk about in a little while and explain what that is, and that's called plasma. So stars are big balls of plasma, and they look like they're on fire, but they're actually undergoing a process called nuclear fusion inside, which creates all this heat and light and different types of energy. And as we know, the sun keeps us nice and warm. So we're going to talk a little bit about the life of a star from beginning to end now. So how are stars made? Has anybody got any idea what these are pictures of, or any ideas about how stars are formed?
Oh, so what do you think those are pictures of, George?
Stars clustering together.
Stars clustering together. What do you think, James?
I have pictures of these in the book, but it's some sort of gas.
Okay, thank you. Lola?
Is it a constellation?
Thank you.
Constellation.
Constellations?
It's like when stars go together, they can make like animals and shapes.
When stars come together, they make different shapes. Yeah, Emma?
A star being made, so it could be the star dying.
Oh, a star dying or a star being made. Does anybody know a kind of name for some of these sorts of pictures? Lola?
Is it a galaxy?
Galaxy? Anyone got any ideas of names of what?
Milky Way.
Maybe the Milky Way, Sunny?
Nebula.
Nebula. Okay, let's see what Jacqueline says.
Oh, that's fantastic. Some really interesting answers there. So, yeah, somebody said nebula. These are nebulae. So they're clouds of gas and often dust. So somebody mentioned they're big clouds of gas, so that's right. Somebody said there about them reminding them of shapes of animals, and it's true that a lot of nebula are named after animals. So we have things like the Eagle Nebula or the Crab Nebula because they remind us of animals. And there are lots of these. They're interstellar, which means in between the stars, clouds of gas and dust. And when we talk about how the stars are made, these are very important because all of these little particles of gas and dust, they're drawn together in space because of gravity, just like the gravity that sticks you to the floor. All these little particles want to move together, and they get closer and closer, and they collapse down and become more and more dense. And we think that in the early stages of the universe, after the Big Bang, that most of the matter or things that things were made of in the universe were mainly hydrogen and helium gas. And so these particles would have been floating around, and there wouldn't have been much else. But eventually they would have clustered together because of gravity and started to get closer and closer and into a smaller space and denser and denser. And this is really important in how stars are formed. So we're going to talk a little bit about matter. Has anybody done any studying of matter and can tell me a little bit about the atom at all?
Well, do you know, James? Come on.
My mum's that sort of person, and she tells me a bit about it, but I'm not such as much because I know electrons and neutrons.
You've heard of electrons and neutrons, and your mum talks about it, does she? Yeah.
Is it like lava, but really hot lava, what like killed the dinosaurs, that big meteor, but it broke up into little stars?
Oh, that's interesting, Lewis. Anybody heard of protons, neutrons, electrons before? I think a few people have heard of them, but perhaps we don't know much about this, Jacqueline.
Oh, that's really interesting. So everything is made of atoms. We didn't know this because they're very, very, very small. And we'll talk about this later tonight when we look at the scale of the universe and how small things can be. But they're tiny, and they're actually mostly made up of empty space. But in this diagram I'm showing you here, this is just a sort of diagram to show you what it kind of is made of. But it's very difficult to actually really draw an atom in the way that it really is, because they're very strange things. And they're ever so tiny, and everything that we can see and touch, the air that we breathe, everything you can think of is made of these atoms here on Earth. There are some other types of matter about in space, and we can talk about that maybe in another hangout that's a bit more complicated. But everything we know of is made up of these atoms. And inside these atoms, you have the nucleus in the middle, which will contain a proton and often neutrons. And the proton has a positive charge. So pro means positive. And neutrons have a neutral charge. And then the electrons, which circle around, you can think of them as circling around the nucleus, they have a negative charge. And so this little atom just can connect with other things and make up bigger types of matter like molecules. But all of the atoms we know have different numbers of protons in the nucleus and different numbers of neutrons and electrons. And together, when we put them all together, we can put them into a chart which will tell us a little bit more about them. So has anybody ever heard of the periodic table?
Yeah, lots of hands up for that.
Oh, fantastic. That's really good. So if you're interested in chemistry and physics and biology, really, you will need to learn a little bit more about the periodic table. The history of the periodic table is really interesting. And again, I think we should probably have another talk about that. But you can think of these charts and numbers here with the numbers on them showing you how many protons are in the nucleus. So as we go along and the nucleus gets bigger and bigger, we get chemical elements. So this is the periodic table of elements, and elements make up everything. They're sort of like the bricks that build things, and they're made up of protons, neutrons, and electrons. And when they join together, they can make molecules and then make everything that we can see and touch. So they're really interesting. And the two really interesting ones that I told you about are hydrogen and helium. And these are the ones that we think made up most of what the universe was made of in the early universe after the Big Bang. So hydrogen on the top left there, you can see that's got a number 1, and helium on the top right has a number 2, and that tells you what's inside the nucleus of the periodic table of the different elements. So here's a diagram of them. So you can see hydrogen there has 1 proton in the middle and then 1 electron orbiting around it. And then helium has 2 protons, 2 neutrons, and 2 electrons. So that's why they sit in that part of the periodic table. And as you get to bigger and bigger, heavier elements, they'll have more and more protons inside, more neutrons, more electrons. And there's a whole lot you can learn about the periodic table. And it's really important if you want to study something like chemistry or biology to understand how these things look and why they like to bond together. But yeah, the periodic table is fantastic, and it's a really simple way to visualize what all these elements look like and how they relate to each other. And then we can even tell about how their behavior and what sort of qualities they might have based on what we know is inside the nucleus. So hydrogen and helium are really important, because in those big early gas clouds that were full of hydrogen helium, they would be what we call stellar nurseries. As they collapse together and the hydrogen helium wants to come and stick together because of gravity and get denser and denser and denser, they start to bump into each other and then get closer and closer to the point where these massive balls of gas form that have so much pressure and so much gravity acting on them and are creating really high temperatures in their core that they actually start to create nuclear fusion. And this is what makes stars shine and emit energy in various different forms, but heat and light is one of the ones that we see on a day-to-day basis, but also emits energy in other ways. So that's one of the reasons we have to put on suntan lotion, because we don't want to get ultraviolet light on our skin. And there are X-rays and gamma rays and all sorts of types of energy coming out of the sun, and most of that we're protected from because of our atmosphere and our magnetic field here on Earth. But in space, all this energy just gets to shine out and move across the universe. So these stellar nurseries are where stars are born. So stellar is a word we use to describe stars. And so we think that in the early part of the universe, all of the stars would have been made up of hydrogen and helium coming together and getting high enough pressures and temperatures to undergo nuclear fusion. So earlier on, I mentioned this 4th state of matter, plasma. So the 3 states that we'd be most familiar with day to day are liquids and gases and solids. So those are the 3 states of matter that we know very well. And matter can move through these different states. And we see that very clearly with something like ice. So if you have a block of ice that's in its solid state, and then it will melt if you warm it up and become water, and then it's in its liquid state. And then it will become a gas if we boil it to over 100 degrees Celsius, and then it will become a vapor, and then that's a gas. So we're quite used to this, but there is this 4th state of matter, plasma, which we don't generally see day to day because it requires lots of energy input. And what plasma is if we think about our diagram of an atom, the energy that's coming into the atom is high enough that it will strip away that electron that was orbiting around the nucleus, and that electron is now free to move around. And you actually do get to see plasma lots of the time. So has anybody got a plasma TV or ever watched a plasma TV?
Yeah, quite a few.
Yeah, and also you might be familiar with these sorts of things, these sort of plasma balls that you get to play with in science museums, or neon signs that you see lighting up outside shops and stuff. And this is plasma, and obviously we use them for various different things, and it's that we've put so much energy into the atoms that the electron has become free. And so we call this the 4th state of matter, and that's what's going on inside stars. So the electrons are free to move around. So inside our sun and other stars that are around about the size and mass of our sun, we have this special type of reaction called the proton-proton chain. And what happens here, it's quite complicated, but you can think of it as all of these nucleuses of these atoms bashing into each other all the time and under these huge pressures and temperatures. And eventually they start to combine. And what's going on inside stars is that hydrogen with the 1 proton in its nucleus is being converted into a bigger element, into helium, with 2 protons in its nucleus. So there's various different stages to this, but you basically have individual 1 proton nucleuses bashing into each other, and they'll build up and become a bigger nucleus with 2 protons and 2 neutrons inside. And now you've made yourself a helium nucleus. And so this is what goes on inside smaller stars like our sun. And you end up with the helium in the middle and the hydrogen on the outer shell. And it's every day just converting all of this stuff. Some of this takes a long time, millions of years. Other parts of the process take just seconds. But over time, you will be converting your very light hydrogen element into a slightly heavier helium element. And this creates a huge amount of energy. And that's why stars shine, and that's why they emit all this energy. Also, you have, so this is a picture of our sun. So this is the kind of reaction that's going on inside of our sun. This proton-proton chain is really reserved for the smaller stars that are up to about 1.3 times the mass of our sun. But in bigger stars that are far bigger, there's a lot of stars that are way bigger than our sun. And I'll show you some pictures in our talk later tonight about the scale of the universe to see how big some of these stars can get. But you have a slightly different cycle, the CNO cycle, which stands for carbon, nitrogen, and oxygen. And you have a different chain of events, but the same principle is going on. It's fusing smaller elements into bigger elements and increasing the number of protons in the nucleus. Now, the important thing about this is that it is emitting a lot of energy, and nuclear fusion is something that we don't really know how to use here on Earth to create energy. You need a huge amount of energy to do it, and obviously stars are very big, and so the way that we create energy using nuclear power here on Earth for nuclear power stations is a slightly different chemical reaction, which is nuclear fission, which is splitting bigger elements down into smaller ones. In stars, it does it the other way around, from smaller to bigger. And as it does this inside these bigger stars, it starts to create new elements because it's getting heavier and heavier and heavier. And as far as we know, inside stars, it can get up to about iron, which is the heaviest element it can make inside a star. And after that, there's not enough energy to make anything else. And eventually you'll get these shells build up of these different elements slowly being created and fused together and built up inside the stars until the star runs out of fuel, because it's used up all of its hydrogen and helium, and the various other elements have been made all the way up to iron, and that's where that reaction stops. So what happens when it runs out of fuel? So when stars die, all sorts of things can happen. So I've got a diagram here. Has anybody ever heard of any of the things on this diagram? Anybody heard of like supernova or black holes or white dwarfs?
Yeah, everybody's pretty much got the hand up.
Oh, fantastic. That's really good. So all of these strange and wonderful objects are things that happen to stars when they die. So on that top route there that you can see going across the top here, this is what will happen to our sun eventually, because our sun's a pretty average star. And it will eventually use up all of its hydrogen, and it won't have anything else to burn, and it's not big enough to make any bigger elements. So it will run out of its fuel, and it'll expand, and its shell will start to expand out, and it will become what they call a red giant. I'll show you a chart in a little bit of all the different types of stars there are, but we use giants to describe very big stars, and dwarfs to describe much smaller stars. And eventually, after the dying star swells up and expands out, and also it gets a little bit cooler, it will shed its outer shell, and then you're ended up with a little white dwarf in the middle, and sometimes a planetary nebula around the outside of all of the matter that is shed from its outer skin. And now it's a white dwarf. It's finished doing its nuclear fusion, and it's just sitting there. This sort of like, almost like the embers of a fire. So after your fire has burnt out and there's no more flames and there's not very much heat coming out, you'll have this sort of ember in the middle. And you can think of it almost like that, of the dying middle of what's left inside the star. But white dwarfs are very, very dense. So although they're much smaller than the original Star Wars, they're very dense and very full of gravity, and they're these tiny little very dense objects. And neutron stars can be like that as well. So these are just like the end result of after the star has eaten all its fuel. However, if you have a more massive star, like on this bottom route here, and you have a big star, sometimes rather than just turning into a red giant and then slowly fading into a white dwarf, they will actually explode. And so supernova is a term you might have heard for when stars explode. And these are really energetic things that happen in space, and we can witness them. There's lots of people whose job is to try and track down when these have happened, because all of a sudden you'll see very bright light in the sky. And I'm actually going to show you an example of one that was extremely bright. But these happen all the time, and they're very useful because they can teach us about what's going on in the far reaches of space. Scientists use how bright they are when they explode to try and work out the size of the universe and how far something away it is, something is when it explodes. And then eventually, once there's been the explosion, sometimes all of the matter will collapse down onto itself and suck into itself. And there's so much of it that this thing becomes so dense and so full of gravity that it becomes what we call a black hole. And we call it a black hole because we can't see it. It doesn't emit any light. The gravity is so strong and things are so strange that are going on there that nothing can escape from it. And you might have heard the term event horizon. And this is the boundary around a black hole from which nothing can escape. And we think that even time can't escape from it. And that if you were to try and fly into a black hole, time would change and slow down. And we've got no idea what might happen if you go inside. But some people think you might almost turn into spaghetti. We have this term called spaghettification, where things get pulled into long strings. But I'll leave it to say you probably wouldn't want to go on a journey through a black hole. In movies and stuff, they often do it and strange things happen. But I think if you went in there, you wouldn't come back out. And we think that maybe black holes are in the middle of galaxies, and it might be the object that everything is circling around. But they're really interesting, and we don't know that much about them because we can't really see them. So we have to try and understand what's happening from the energy that emits from them, from looking at the objects that are orbiting around them and how they move and what happens to them, because you can't actually see any light from them. So they're really interesting objects, and they're the end result of what happens when there is a really big star that dies and supernovas and explodes. What's interesting about supernova is that, as I showed you before, inside these big stars, it only gets up to iron on the periodic table when it's making the elements. So you might ask yourself, well, what about all the rest of the elements that are above iron? Well, we think that when stars supernova, this huge amount of energy and all this pressure that's happening from this explosion is where all these bigger elements are made. So this is just an artist's picture of what might be happening after a supernova. And we think that all those sort of shock waves from this big explosion might be enough to pressure all of the elements that are coming out of the exploding star to get bigger and bigger and undergo more nuclear fusion and become bigger and bigger elements. And then it sort of spits out its guts across the universe, and all of this stuff goes everywhere. So what we think is that the earliest stars that were just made from helium and hydrogen from the beginning of the universe, we think that all of the elements that we know today were made inside stars. So that first generation of stars would have only been made of helium and hydrogen gas. But as they built up and made all these new elements and spat them out when they died, that's where all of the elements that we know today came from. They were built inside stars, inside this beautiful furnace in the far reaches of space over billions of years, pressuring all of these elements to get bigger and bigger and then spew out across the universe. And then what happens then is you can get solar system formation. So somebody mentioned earlier about animals, and we've been talking about supernova. So this is the Crab Nebula, and this is what was left over after a supernova. And interestingly, we actually have evidence of when this happened, because about 1,000 years ago, people wrote down that there was suddenly a really bright light in the sky. And in China, some astronomers said that it was so bright that even at nighttime, you could read a book by it. It was so bright in the sky. So we have the date of when that happened. And since that, scientists have looked at this Crab Nebula and watched it over time to track its movements, and then use computer models to track back and make that cloud contract back to a point. And it seems to be in exactly the same part of the sky where ancient astronomers said they saw this bright light. So humans saw this one explode. And so left over here, you've got all of the dust and gas and other elements that have been spewed out from inside the star that died. And we think that that's how solar systems form. So here you have like a star that's died, it spat everything out, and then all of this dust and cloud is now in a nebula, and then they start to come back together again, just like the original gas cloud did of hydrogen and helium. And they get closer together and they bash into each other, and in the middle, all of the hydrogen and helium will come together and start to make a new star burning that's going to start this whole process again. But you've also got all these heavier elements that are circling around, and we think that eventually they bumped into each other, gravity pulled them together, they started to circle round and round, and eventually you get a solar system. So we believe that everything that we can see and touch, you, me, your desk, footballs, animals, you name it, everything is made up from what was inside these stars. So there's a very famous astronomer called Carl Sagan, and I encourage you to watch the Cosmos series. It's on YouTube if you're going to watch it. He talks a lot about all different types of sciences, and he says we're all made of star stuff. People have also said that the atom is the universe's way of knowing itself, because we are made from the things that are inside stars. So you can look down at your hand right now and touch your hand and think of those atoms. At some point, billions of years ago, they were made inside a star. You were made inside a star, and that's true of everything. So this is, mind-blowing stuff. It's really interesting. But without those first generations of stars that built up these elements and died and exploded, we wouldn't have the planets, and we wouldn't have life, and we wouldn't have us. So it's really, really cool stuff. So we think our sun is probably about a third generation star that's gone through this a few times. Our star's so small that it won't supernova, but it will turn into a red giant. But I wouldn't worry, because we've got about 5 billion years left of fuel in the sun, so it's not going to turn into a red giant anytime soon. So we've been talking about different colors and stuff, and we believe that the color of a star is very closely related to its temperature. So that can tell us a lot about what's going on. When we look at stars just with our eyes, we can kind of understand what temperature they might be from the reactions that are going on and what light they're emitting. So we talked about red giants. You also get red dwarfs, and so the temperature is related to how hot it is. When you burn something, if you've ever seen a piece of metal heated up, people might be like, oh, careful, that's red hot. Like, don't touch it, it's red hot. And that's because when it gets to a certain temperature, it will start to emit light in certain wavelengths, and you'll see a particular color. And it's funny that we say, oh, watch out, that's red hot, because red is actually one of the coolest ones. Then it moves through orange and yellow, and we're getting up to 6,000 degrees here. And then white hot, you might have heard somebody think white hot, that's even hotter. And then you finally get up to blue white. And so these are similar to the colors you see in the rainbow. They're different wavelengths of light, and it can tell us about the temperature. And so when you heat something, you will often see, if you ever watch any videos of somebody who works there, somewhere where they're heating metal, you'll see it go from red to white, and that's it moving through the different temperatures and emitting at different wavelengths. And then the stars can be all different sizes as well. What's interesting is that when you have a very big star that's burning very hot in the sort of white and blue region, they don't live very long. They have much shorter lifespans than the smaller, cooler orange and red ones. So we think that blue and white giants will burn out much more quickly, whereas red and yellow stars will last for billions of years and have a lot of time to work through their fuel. So it's a bit like if you had a fire and you made a really big fire and you gave it lots of fuel, but you kept it going and you poured petrol on it, it would burn through its fuel much quicker than maybe a piece of coal that was sitting and slowly burning and not giving off anywhere as much heat or light, but it will last longer. So, when we have a barbecue, we don't want to just have a big fire that burns out really quickly with lots of petrol. We want a nice slow burning coal fire that is more gentle and emits less energy but lasts a lot longer. So you can kind of think of it a little bit like that. So all these different types of stars, they go on to the stellar classification chart. And this is quite a complicated chart, but really you're seeing here on the sort of up and down axis here, you're seeing how bright the star is. And then we divide all the stars into these different categories I don't know why in astronomy, they often have these things that are not very easy to remember. But our star is M class and sits about there on the chart. And so there's different types. You've got white dwarfs, you've got your red dwarfs, you've got hypergiants, supergiants, bright giants. Main sequence over here, and this is where our star lives. It's a main sequence star. And then here on the bottom right, you've got brown dwarfs, which are really interesting. Has anyone ever heard of a brown dwarf?
Brown? Have you ever heard of that? Getting lots. Oh, 3 people have got their hands up.
Oh yeah. Any idea what it might be?
What do you think it might be? George, you had your hands up?
It's like a star that has died away quite a while ago.
Star that died quite a while ago. Anyone else want to make a guess? Harvey?
Is it like a star that's still alive, even though it should have been dead?
Let's hear from Freya.
I think it's quite near to the inside of the star.
Near to the inside of the star. those are our ideas.
That's really interesting ideas. So brown dwarfs are a really interesting one because they're kind of halfway between a planet and a star. So we talked about the stellar nurseries and how all these elements come together and like get bigger and bigger and squish together. But you know, that's how the planets are formed too, right? That's lots of like dust and gas coming together and squishing together to make a planet. So why don't planets shine? And it's because they're not massive enough. What's interesting about brown dwarfs is they are kind of in that halfway mode where they're not quite massive enough to really shine like a star, but they're too big to just be a normal planet. And so our biggest planet is Jupiter, and that's nowhere near big enough or massive enough to start shining. But if we made Jupiter, I think it's about 13 times more massive, then it would start to very gently try to start nuclear fusion in its core. And it uses a slightly heavier version of hydrogen to do it inside its core. And it shines very weakly and dimly. And it's not a true star, but it's not a planet. And so they've got their own name, this brown dwarf, which is just on that cusp. It's never quite made it to a star. If it was a bit bigger, it would, but it's a little bit too big to be a planet because it's undergoing some reactions in its core. So they're really interesting. And people had thought that these might exist, but we've actually got images of some of them now, and they're very difficult to find because they don't shine very brightly like stars. So here you've just got the, I showed you that chart with the different classifications. So our sun is an M-type star sitting down here in the bottom. So it's really quite a small, ordinary star. And then as they get bigger and bigger through the different classifications, they get bigger and whiter and brighter. And then the biggest type here is the O-type. So yeah, you've got all these different types, and you can learn a lot about what's going on inside a star by what color it is, how brightly it shines, and that can tell us something about how far away it is, because if we know how brightly it shines in reality and how bright it looks to us in the sky, we can kind of work out how far away it might be. So it's quite interesting for learning about the state of the universe. So I wanted to ask you, have you got clear skies there tonight? Are you going to be able to go outside and look at any stars tonight?
Yes, hopefully.
Yes. So that would be fantastic. If you can go out and look at the stars, you can actually see some of these different types of stars. So at this time of year in the winter, we've got the Orion constellation, and that's an interesting one to look at because it has some of these different types of stars in it. So Orion is named after mythology for the hunter because, and I mean, they've joined up the lines here. So it's supposed to look a little bit like a hunter holding a bow and arrow, but, you know, different places and different people have joined these up in different ways. So there's lots of, we have our classic sort of mythology that we look at with the Greek and Roman stuff to make these up. But if you look at other cultures, people have done different types of drawings, but it's a very common thing through human history to see patterns and make stories to do with their ordinary lives, their gods, and they will name them after them. So Orion is the hunter. And this is Orion's belt. You might have heard of that. There's these 3 stars across the middle. And I'm particularly interested in Orion's shoulder down here and his foot down there. Because if you go outside tonight, and somebody mentioned this star earlier, you will see on Orion's top left shoulder, you have this star called Betelgeuse. And on his bottom right foot here, you have this other star called Rigel. And these are 2 types of stars that are pretty easy to see in the night sky. And you can actually see their colors. So Rigel is a blue supergiant and Betelgeuse is a red supergiant. So they're very big, very bright stars. And Betelgeuse is an interesting one because we think that Betelgeuse is on the verge of dying. We think it's about to give up the ghost and let go. And because it's so far away, and again, we'll talk about this in the scale of the universe, you don't immediately see the light from something. It takes a very long time to travel. And so we think Betelgeuse is about 600 light years away. So that means it would take over 600 years for light to travel at the speed of light, which is very, very fast, to get here. So when you look at the stars, you're actually looking back into the past because we don't see what's happening straight away. We have to wait for that light to travel to us. And that's true even of our nearest star. It takes the sun about 8 minutes for the light to get here. So any changes on the surface of the sun, you wouldn't see for 8 minutes. And in Betelgeuse's case, it would take you hundreds of years. So Betelgeuse might have already died. And we don't know yet. So we'll have to wait. And it might be that in our lifetime, if we're lucky, we might see some changes to Betelgeuse. But I think it's an interesting one to look at because in this photo, you can actually see, and you should be able to see this if you have a clear night tonight, you should be able to see the color difference, and you'll be able to tell what temperature this star is at and what type of star it is by looking at the color. And you should be able to see that Betelgeuse has got a red tinge and Rigel's got like a bluey tinge. So I hope you get clear skies tonight. Look out for Orion's belt. That one's quite easy to position yourself and see what you're looking at. You see those 3 stars in that diagonal line, and then look up to the left shoulder and down to the right foot, and you guys can let me know if you've managed to see those colors for yourself. And that's true of lots of different objects. So have a look. If you're ever lucky enough to see Mars in the sky, you can see the red tinge of Mars, and we can tell a lot about objects by the colors. And as you look around, you might see some other stars that you can see the colors of too. Also have a look out for Polaris that someone mentioned earlier, the North Star, and there's lots of other constellations which I'm sure if you've had a look at some of the star charts you'll be able to recognize some of them. But it's important to remember that just because we've put these in a pattern as humans and joined them up, it doesn't mean they're actually near each other in space. They could be very, very far apart. One could be way in the distance and one way in the foreground, but these are the patterns we see. And I think it's always interesting to see if you can come up with your own patterns and decide what's important to you and make some of your own constellations. So that might be a fun thing to do. And I think that's about all I've got to say about stars. So we've gone all the way through from the beginning of their birth in stellar nurseries, through their evolution and nuclear fusion, and to their eventual death after they've done us the service of making all these chemical elements and spitting them out so that we can be here today. So we've got a lot to be thankful for stars. And yeah, I think that's about all I've got to say. So I'll stop screen sharing so you can get rid of this horrible thing and come back to me. So yeah, that's all I've got to say about stars. Has anybody got any questions that they'd like to ask?
I just have to apologise, Becky, because Emma has had to go and pick up one of our visitors.
Oh, no problem. That's fine.
Does anyone have any questions? We've got hands going up here. Freya?
What is a zodiac constellation?
Say that again, Freya.
What is a zodiac constellation?
What is a zodiac constellation?
Okay, so this is really interesting. So throughout human history, as I said, people would name these different patterns after things. And in some cultures, people would come up with different stories and mythologies of what these things mean. And so you might be told if you're born on a certain day. So my birthday's in July, and so my birth constellation is Leo, the lion. And so Leo is one of the constellations that we use to make these patterns in the sky. And it's all about the time that you're born and where the stars are in the sky, because obviously Earth is moving and spinning and tipping. So you can see different constellations at different times of year and depending where you are on the planet. So at the time that you were born, you can look up and see on your birthday where the stars are in the sky. And this is how we decided to tell stories about what it means when you're born. So some people might say that if you were born in July and you're a Leo, that you might have the characteristics of a lion and that you would be strong and proud. And then other people might say if you were born in the zodiac sign of Cancer, the crab, that you might have a hard exterior, but inside you're soft. But then, you know, if you get in an argument, you might be a bit pinchy or whatever. And so there's all sorts of different things. And there's stories about related to the mythology of what's in the skies relating back to your birth. Lots of people live by this and are very interested in it. And I think it's a really important part of our culture and our history. I don't believe that the stars have an everyday effect on your life. They're so far away that they say that the gravity of the people around you when you're born is actually stronger affecting you than the planets or the stars really far away. But I think it's very interesting, and a lot of people are very interested in it because it's about people trying to understand their lives and understand the night sky. And a lot of our early history of what we knew about the universe and our attempts to map the stars came about because of the zodiac and because of people believing in these stories. And it's all part of our history. So I find that some scientists might look down on people that are interested in the zodiac, but I think all of it is a way of us understanding ourselves and the universe. And as I said, we are part of the universe. We are made of these things from inside stars. And while I don't believe that zodiac signs have an effect on our day-to-day lives, I think it's an interesting part of history and culture, and it's something that gets people interested in the way the stars are moving, which is great. So you can look up your birthday and when you were born, and you can decide for yourself if you think you have the characteristics of your zodiac sign. But I think you'll find, for me, when I look through the horoscopes and predictions, that you can apply most zodiac signs to most people. All of us have a little bit of everything in us, because the stories of the zodiac come from human culture, and we all have those sorts of things in common. But it's interesting stuff, and the history of it is fantastic. So there are 12 zodiac signs. So you probably know them, like Leo, Sagittarius, Cancer, Libra, and so on. And there was actually a 13th one. I can't remember the name of it off the top of my head, but for some reason that one got left out and is gone from modern horoscopes. So that's an interesting one as well. Any other questions?
Thank you. Olivia,
Do you know how many stars are in the sky?
do you know how many stars are in the sky?
Oh, that's a great question. There are a lot. I don't know the exact number. You have to bear in mind that the ones we can see are the ones that are bright enough that the light can reach us. And also some of the stars that the light is reaching us, undoubtedly those stars are not there anymore. They've died, but it's taken so long for the light to reach us that they're no longer there. But in our galaxy, which is our local group of stars, the Milky Way that we live in, there are 100,000, I think about 100,000 stars. And in our next nearest galaxy, in Andromeda, we have about 400,000 stars. And then later, when I do the Scale of the Universe talk, I'll show you some of the images from the Hubble telescope, which show how many galaxies there are. And each one of these galaxies contain hundreds of thousands or millions of stars. And it seems that there are millions and millions of galaxies. So my answer would be that there's almost an infinite number of stars, and we don't really even know how big the universe is, and I'll talk a little bit about that later. We have to talk about the observable universe of what we can see. So you can basically think of the number of stars as infinite, but I'm not sure how many stars we can see in the night sky. There is a catalogue. Somebody has, over time, people have written down how many we can see, but there's more than you can ever count in your lifetime.
Thank you so much. We are going to have to go now.
No problem at all. Thank you for the wonderful questions. It's nice to be able to present on something a bit different than planets. So I'm looking forward to our talk later tonight.
Thank you so much.
Thank you.
Thank you.
Bye.
Bye.